Alright, so in today's tutorial video, I want to look at statistical methods for analyzing two sample data in Python using Jupyter Notebook. But before we proceed, I'll urge you to kindly take a look at my previous tutorial video on the flowchart for classifying data, because in that video tutorial, I illustrated and explained the data structure for two sample data, which will help you to catch up with everything that I'm going to do in today's tutorial video. Okay, you can just click on the link in the card above or check the link in the description of this video. Alright, so like the one sample data, we have parametric test and non-parametric test for analyzing such data. The same applies with two sample data. The type of parametric test for two sample data is known as the two sample T-test or the independent T-test. This test basically compares the means of two separate groups to determine whether statistical evidence shows that the associated population means are significantly different. Okay. For example, researchers may wish to compare the mean income level of two regions or the mean effectiveness of two drugs. There are certain assumptions which must be satisfied before this test can be used. One of the assumptions is that the data must be continuous. The next one is that the two samples are independent. The third one is that the data must be normally distributed. And the fourth one is that the variances of the two populations are equal. This is an asterisk because even if it is not satisfied, we can still go ahead and make use of the two sample T-test. We just have to specify in our computation that the variances are not the same. Okay. Now let's take a look at the non-parametric test for two sample data. This is known as the Mann-Whitney U test or the Wilcoxon Rank Sum test. This test basically compares the medians of two separate groups to determine whether statistical evidence shows that the associated population medians are significantly different. Okay. So for example, researchers may wish to compare the median income level of two regions or the median effectiveness of two drugs. So there are certain conditions which must be satisfied before this test can also be used. One of the conditions is that the data must be continuous. The next one is that the two samples are independent, and the third one is that the data must not be normally distributed. Okay, let's take an example. As a researcher, you wish to compare the average sepal length of the Setosa and Virginica plants from the iris dataset. Perform statistical analysis for this data. Alright, so before we jump into our Jupyter Notebook, let's take a look at the iris dataset in a CSV format. So this is a clean data. Okay, before you analyze any data set, you have to ensure that you have cleaned it. So let's assume this is already a clean data, and if you want to learn how to do data cleaning, you can just check out my video tutorial on expert data analysis in Python. Okay, you can just click on the link in the card above or check the link in the description of this video. So we want to find out if the sepal length for Setosa and Virginica are the same or not. So first of all, we want to filter the sepal length for Setosa, which starts from here. So we have to filter this, right? And I think it ends somewhere here. Yeah, it ends here. Then we also have to get the sepal length for that of Virginica, starts from here. Okay, Virginica. Then it ends somewhere here. I think the last one, of course. Okay, and try to find the average value for this and compare that to that of the average value of the Setosa. Okay, so we want to find out if these average values are going to be the same or not, or basically we want to find out if the difference in the average value is equal to 0 or it is different from 0. Okay, so let's jump into our Jupyter Notebook. Alright, so the first thing that I want to do is to load a library which will be used in our data imputation as well as some of the analysis, which is the pandas library. If you want to learn how to install some of the libraries and also how to work with them, you can check out my video tutorial on explorative data analysis in Python. You can just click on the link in the card above or check the link in the description of this video. Okay, so first of all, you have to have this installed, the pandas, before you can import. Okay, so I want to import pandas as PD. Let's run this. Okay, then we can proceed to load our data set. I want to assign my data set to IDAT. Okay, so from pandas, I'm making use of the function read underscore CSV because my data set is a CSV form. This is the function that I have to use, and the name of the data should be in a form of, it should be in quote. Okay, so clean data.csv. I'm going to leave this data file in the description of the video so that you can also download it. And you have to ensure that this data file is in the same folder where you have your Python source file or script file, so that you wouldn't have to set a new working directory. Okay, so if you check this, let me see. So I have my Python source file and the data file in the same folder. Okay, so this will make it easier for you to work with. So let's run this. Alright, so once it's done, we can then view our data set. Alright, so let me ignore the head. Let's view it. Alright, so this will basically display the data set in a spreadsheet form, giving us the first 5 observations, right? And also we have the last 5 observations. Let's check the structure of our data set. So we can see that we have 148 entries starting from 0, index 0 to 147. And we also have 5 columns, right? Which the first one is SIPA length. We also have SIPA width, beta length, and beta width, and they are all flow 64, which is basically numeric, but species is an object, which is basically a character or a string. So in our data manipulation, we are supposed to encode this by converting it from string to numeric. Okay, so let's quickly do that. So in our data manipulation, we want to recode a species from string to numeric, or basically convert it into a categorical variable. Okay, so for my data IDAT, I want to pick the variable species, and I want to basically convert the data type as a category. Okay, so let's try and run this. Alright, so now let's get a structure of a data set. So we can see that species has now been changed into a category. Okay, so we are good to go. The next thing that we want to do is to basically rename the variables. This is optional, you can skip this if you wish to. So I want to rename our variables, and I want to assign my data now to new dat. So basically we are interested in the columns, and the SIPA length we want to rename it as SL, the SIPA width as SW, petal length as PL, the petal width as PW, and species as SP. Okay, so let's try and run this. So okay, so we are good to go now. Then let's check the structure of our new data set. Alright, so when you scroll down, you can see that the name of the columns or the variables have been renamed. Okay, the next thing that I want to do is to filter the SIPA length of the Citosa and also filter the SIPA length of Virginica. Okay, so in our data filtering, I want to start with that of the Citosa. So I want to assign my data. To G1 underscore SL. So for my new data, I'm picking the species variable, and I'm interested in the label Citosa, and also I really want to pick that of the SIPA length. Okay, and also to view the first 5 observations. Okay, let's try and run this. So here we go, we can do same for Virginica. So Virginica, my data is now G2 underscore SL. Okay, and these are specifications. So let's run this. Alright, so now that we are done, the next thing is to basically do some exploratory data analysis on this data to know whether we are going to make use of the two sample T-test or the Mann-Whitney U test. Okay, but this will be similar to the one that we did under the statistical methods for analyzing one sample data in Python. Okay, so I want to skip this session of the exploratory data analysis. Okay, from the exploratory data analysis, we got to know that the distribution of the SIPA length for Citosa and that of Virginica were approximately normal. Okay, or they were symmetric. Okay, we also got to know other useful numerical summaries as well. So if you want to learn how to do the exploratory data analysis, you can just check out my video on the statistical methods for analyzing one sample data in Python. Okay, you can just click on the link in the card above or check the link in the description of this video. Okay, so because they will be the same, I don't want to waste time on that. So let's proceed to the other steps, which is basically to check for the assumptions. Already we know that this data is continuous. If you look at the values, they are continuous, and also we can see that they are independent because the SIPA length for Citosa is different from the SIPA length for that of Virginica. These are two different species plant. Okay, so this makes them two independent. The next assumption that we want to test is the normality assumption. So let's quickly do that. So test for normality assumption, we want to make use of the QQ plot. Okay, the QQ plot basically draws the correlation between a given sample and the normal distribution, such that if the data is approximately normal, then the plot will closely resemble a straight line sloping upwards to the right. Okay, But before we make use of the QQ plot, we need to load some library. So we want to import the CPy start as SS and also import the pipe lab. This will be very useful in visualization of the QQ plot. Okay, so let's try and run this. Alright, so the first thing is to get a QQ plot of the CPy length for Setosa. So I want to assign my plot to Q1. So from the CPy start library, I'm using the function prop plot. Okay, and this is the data for Setosa, and I'm interested in the variable CPy length. Then the distribution should be normal, and the plot should be pile up. Okay, so let's try and run this. Alright, so we can see that most of the points are on a straight line sloping upwards to the right. So this is an indication that the distribution of the CPy length for Setosa is normally distributed. Okay, let's check that of the QQ plot of the CPy length for Virginica. So now I'm assigning my plot to Q2, and this is the data for Virginica, the CPy length variable, then everything follows. So let's run this. Alright, so we can see here that some of the points seem to deviate from the straight line, but majority of the points are on the straight line sloping upwards to the right. So we can also say that the distribution of the CPy length for Virginica is normally distributed. Sometimes you may have some doubt with regards to this visualization of the QQ plot, so it's good to make use of other tests of normality like the Shapiro-Wilk test and the Anderson-Darling test. Okay, so let's check other tests of normality like the Shapiro-Wilk test and the Anderson-Darling test. The null hypothesis for this test states that the distribution of the data is normally distributed. Okay, so before we make use of this test, we need a library. So from the CPy start library, we have to import the function Shapiro, and also from the CPy start library, we want to import the function Anderson. So let's try and load this. Alright, so the next thing is to basically check that all the Shapiro-Wilk test of the CPy length for Setosa, and the second one will give us the Shapiro-Wilk test of the CPy length for Virginica. So let's try and run this. Alright, so we are interested in the p-values. So if you look at the p-value for the Shapiro-Wilk test of the CPy length, right, for Setosa we can see that is 0.325, and also if you check that over Virginica is 0.253. If you have to compare these p-values to the alpha level or the threshold value at 1% or 5%, it means that we will fail to reject the null hypothesis. We only reject the null hypothesis if the p-value is less than or equal to the alpha level of significance. Okay, but now because the p-values are greater than the alpha level at 1% or 5%, it means that we fail to reject the null hypothesis and conclude that the distribution of the CPy length for Setosa and that of Virginica, right, is normally distributed. Okay, both of them are normally distributed. Now let's take a look at the Anderson-Darling test. Right, so the first one will basically give me the result of the AD test of the CPy length for Setosa, and the second one will give me the AD test of the CPy length for Virginica. So let's run this. Alright, so if you look at the results here, we want to compare the test statistic with a critical value at various level of significance, but we want to use the standard one, which is at 5% level of significance, and this is the critical value at 5%, 0.735. And we want to make decision with regards to the test statistic. If we want to make a decision with regards to the test statistic and the critical value, we will reject the null hypothesis if the test statistic is greater than the critical value. Okay, now because the test statistic is less than the critical value at 5% level of significance, it means that we fail to reject the null hypothesis and conclude that the distribution of the CPy length for Setosa is normally distributed. The same applies with that of the Virginica data. If you look at the test statistic, it's 0.565, and if you look at the critical value at 5%, is 0.735. So trying to make inference with this, we can see that because the test statistic is less than the critical value at 5%, we fail to reject the null hypothesis and conclude that the distribution of the CPy length for Virginica is normally distributed. Okay, so now that we are clear that the normality assumption has been satisfied, we can then proceed and make use of the two sample t-test. Okay, So the null hypothesis can be stated as the mean value of the sepal length for setosa and virginica is the same. And alternative can be stated as the mean value of the sepal length for setosa and virginica are not the same. In other words, you can also state the null hypothesis as the difference in the mean value of the sepal length for setosa and virginica is equal to 0. And alternative can be stated as the difference in the mean value of the sepal length for setosa and virginica is not equal to 0. Okay. So before we make use of the two sample t-test, you have to remember that there was one assumption which stated that the population variance must be the same. Okay, so we have to test for that. We call it the test for homogeneity of variances, and we can basically do this by making use of the f-test or the 11E test. Okay, so the 11E test is basically less sensitive to departure from normal assumption, while the f-test on the other hand is often used when the distribution of the two samples is approximately normal. Okay, now in order to make use of the f-test, you have to define or create some pseudocode. You have to basically define some function. Okay, and we need some library import numpy as np. This library is very vital for working with arrays. Okay, so we want to define our f-test function. So this is the name of the function f-test, and we have two arguments. The first argument is x, the second argument is y. So the x input will definitely be in the form of array. The same applies with the y. It will also be in the form of array. Okay. Then this f is basically going to calculate the f statistic. So the numerator, this is going to be a ratio. The numerator is the variance for the first argument, and the denominator is going to compute the variance of the second sample. Okay, so in here we have the delta degrees of freedom to be equal to 1 because we want to basically estimate the population variance using sample data. If we set this to 0, then it means that we want to basically calculate the variance of the population. Okay, so always we set this to 1 for sample data. So this will give us the f statistic, and this is going to define the degrees of freedom, right, for the numerator, and this is going to define the degrees of freedom for the denominator. One thing that you have to note with regards to the f-test is that because the f-score from the f distribution is always greater than or equal to 1, the f ratio or let's say the ratio of the f-test is arranged such that the the numerator, okay, will always be greater than the denominator. So before we make use of this test, we have to check for the variance to know which one of them is larger so that you can place it as the first argument. Okay, so this p will basically give us the p-value and we get our result. So let's try and run this. And then want to compare the sample variance. Yes, you have to compare the sample variance to know which of the variances is large so that we can place it as our first argument. Then the second argument will take the smaller variance. Okay, so let's check that. So if you look at the variances, we can see that the variance of the sepal length for virginica is greater than the variance of the sepal length for setosa. So it means that in our f-test, we are supposed to specify gene2 underscore SL as our first argument, and the second argument will take that of the setosa. Okay, so let's quickly do that. So let me change this gene2, and this should be gene1. Okay, so we want to perform the f-test now. Let's try and execute this. Alright, so if you look at the p-value for this test, this is a test statistic which will be compared to 1. So we want to find out the p-value result. If you have to compare this to the upper level or the threshold value at 1% or 5%, it means that we are going to reject the null hypothesis and conclude that the homogeneity of variance for these two groups is going to be false. Okay, so basically the variance for these two distributions are not the same. Okay, so another way to do or check for the homogeneity of variance is to make use of the 11E test. Okay, so we need a library. So from SciPy start, we want to import the function 11E. So for the 11E test, the first argument is that of the, you can change it, you can interchange it. We don't have to specify. We don't have any specification in terms of the data. Okay, so the first one is basically the data of the sepal length for setosa, and this is the sepal length for virginica. Okay, and in here we have another argument, and we basically specifying the center to be the means. The center is basically looking at the measure of central tendency. Okay, we have three of them. We have the mean, median, and mode. In here, we are using the mean because we know that the distribution is nearly symmetric. If the distribution were highly skewed, we would have make use of the median. By default, the leavening makes use of the median. Okay, but because we know that this distribution are nearly symmetric, that's why we are specifying the center to be the mean. So let's try and run this to see the results. So if you look at the p-value for this test, you can see that if you have to compare this to the alpha level at 1% or 5%, it means that we are basically going to reject the null hypothesis and conclude that the homogeneity of variance for these two groups is false, or basically the variance for these two groups are not the same. Okay, so now that we are clear with what to do, we can then proceed and make use of the two sample t-test. In books, we come across this assumption that the t-test is often useful when the sample size is sometimes less than 30, right? But one thing that you have to note is that the t-test, or let's say the two sample t-test, is a symmetric distribution or a family of cares that is based on the concept of degrees of freedom, which is related to the sample size. So as the sample size increases, the t-distribution approaches the standard normal distribution. So even if you have sample size that is more than 30, you can still make use of the t-test or the two sample t-test. Okay. Alright, so we want to test for the difference in means. So from the CPy-stat library, we are making use of the function, the independent t-test underscore independent. Okay, and the first argument is the sepal length for Setosa, and this is the sepal length for Virginica. And we have another argument which is equal variance. We want to find out if the variance were the same or not. And from the test that we had, okay, we saw that the variances for these two groups are not the same, so we have to set this to false. If they were the same, then we are going to change this to true. Okay, so we can now get the result for the two sample t-test. Let's run this. Alright, so if you look at the p-value here, if you have to compare this p-value to an alpha level at 1% or 5%, it means that we are going to reject the null hypothesis and conclude that there's enough evidence to indicate that the mean value of the sepal length for Setosa is different from that of the mean value of the sepal length for Virginica. Okay, so that is how you can draw your conclusion. Okay, now let's assume that the test for normality failed. Then we are supposed to resort to the non-parametric test and make use of the Mann-Whitney U test. Okay, so let's assume the normality test failed. Then we have to make use of the Mann-Whitney U test or the Wilcoxon Rank Sum test. Okay, so we need a library already. We have already imported this library, so I don't need to run it again. So from the CPy-stat library, we need a function Mann-Whitney U, and the first argument is going to give me the sepal length. This is the sepal length for Setosa, and this is the sepal length for Virginica. Okay, and the alternative is two-sided. Okay, with regards to the Mann-Whitney U test, it is also good that the sample size should be less than 30, but we can skip it for now. The procedure for this test involves pooling the observations from the two samples into one combined sample, keeping track of which sample each observation comes from, and then ranking the lowest to highest from 1 to the last element of the combined sample. Okay, so let's try and run this to see the result. So if you have to look at the p-value, you can see that if you have to compare this p-value to the alpha level at 1% or 5%, it means that you're also going to reject the null hypothesis and conclude that the distribution of the sepal length, or the median value of the sepal length for Setosa, is different from the median value of the sepal length for Virginica. In other words, you can also say that there's enough evidence to indicate that the difference in the median value of the sepal length for Setosa and Virginica is different from 0. Okay, so this is basically how to perform a detailed statistical analysis for two sample data in Python using Jupyter Notebook. Please, if you find value in today's tutorial video, don't forget to subscribe if you have not, and also turn on the notification bell to get more updates anytime I post on this channel. Thank you for watching.